Right, so esters. And if you notice that the quote-unquote leaving group of an ester is an OR group, so the only type of nucleophilic reaction that an ester can undergo, or the nucleophilic substitution reaction, is anything that has a nitrogen nucleophile. And I've drawn that 100 times. I'm not going to draw the mechanism behind that. You should be familiarized with that. What I am going to draw and I am going to talk about, though, is that it can undergo acid or base hydrolysis reactions. The acid reaction is going to form us a carboxylic acid, whereas the base reaction is just going to form, just with any type of ketone or carbonyl, I don't know why I keep saying ketone, carbonyl compound that we're exposing in the presence of acid. We go ahead and start off with a proton transfer reaction. Notice that these are not subtle conditions. These are pretty strenuous conditions that we have to undergo for both esters and for when we talk about amide reactions. I, for one, take comfort in that because esters are what hold together your phospholipid bilayer. It's a phosphodiester bond that's holding together your DNA. So if these type of bonds were reactive, then you wouldn't be existing. Under extreme conditions of acids and bases, we can go ahead and have this proton transfer reaction taking place. And I'm just going to make a note that this does exist in equilibrium, which should kind of give you some patterns to see there. So we have a positive formal charge, and just like we have drawn probably 30 times by now, we have water acting as a nucleophile to stabilize that positive charge. And just like before, I can use water to show that water is a base in this context, but I'm just going to go ahead and change colors. Use my conjugate base of whatever acid I use to catalyze this. Usually hydrosulfuric acid works pretty good. Memories. I hope this seems the analogous structures to what we had in the past, but we have ourselves an acid that was either formed there that we had enlarged because we have catalytic concentrations to make this reaction proceed forward, as you can see by this. And so we're going to have a proton transfer reaction. It's going to happen anywhere, but in this context, the only one that we're interested in is where we have it on the OR group. That's giving us a positive formal charge. I'm just going to go ahead and draw in one lone pair because it's a pain in the ass to draw lone pairs with this pen. But usually you'd think a base would come into this. This is obviously an equilibrating reaction, but a positively charged oxonium ion is a really great leaving group, just like when we had talked about with water, and now we're talking about with it in the context of an alcohol. So we go ahead and have that move, and what we get is formal charge on the oxygen there. I'm going to go ahead and just draw another random conjugate base that's going to do a proton transfer reaction. I didn't draw the bond there, but I think you've seen that reaction happening a bajillion times by now. And so what we get is our carboxylic acid. So this is an acid catalyzed reaction. I've done videos explaining the pKa differences between these in water because that's what we're working with. But yeah, keep that in mind, and that's all there is to that. So the other type of hydrolysis reactions you can do is with bases, with things that are going to give us a high concentration of hydroxide in water. And so we go ahead and run this just like we had talked about with, I think, aldehydes and ketones. It doesn't need to be protonated. It doesn't need to have any type of an acid to catalyze it. I'm going to go ahead and just show that this does exist in equilibrium. Our tetrahedral intermediate, I'm going to go ahead and just draw in one lone pair, and that should be an OR. Don't know how that escaped me, but nevertheless, what goes up must come down, and so the electrons come back down, kicking off the OR as a leaving group, thus forming a carboxylic acid, yeah, in a basic concentration. So I think you can imagine what's going to happen. Either the OR group, or you could even think of it as just another OH group going off and then acting in equilibrium. This being a stronger base than the OH is more likely to do so, so that's why we draw it in the way that we do with a proton transfer reaction here, leading us, because we're reacting this in such highly basic conditions. Again, that's why your body is not falling apart right now. Oh, come on, Robert, you can draw better than that. Just leave it in that format of a carboxylate anion. I hope I don't get a letter for get a no-knock raid done on my apartment, but I don't know if you've noticed this, but there's a certain scene in Breaking Bad, one of my favorite TV shows, that is rifled with scientific inaccuracy, and I think they did that on purpose, because up until that point, the show really was pretty cool, and I thought pretty accurate with their chemistry. But I will leave it at that, just because I don't want to give out any dangerous information. So amides are hands down the most stable carboxylic acid derivative. And it does list these reactions because if you keep in mind Le Chatelier's principle, even in an unfavorable, thermodynamically unfavorable reaction, if I add enough product, enough reactants, I will eventually, after a long period of time, get a reaction. It'll be in extremely low concentrations, and this reaction is extremely inefficient, which kind of makes me wonder why they bothered mentioning it. I guess for biological reasons, this can happen when your body starts to decompose. But let's talk about with amides. So we have either acid usage to break down amides and to convert them into carboxylic acids, or bases that we can use too. So I guess I'll draw out my products here. So we can use with an acid, we can convert an amide to a carboxylic acid, and then if we use a base, we can convert it to a carboxylate anion. But this is a highly inefficient reaction. So I'm going to draw out the mechanism. I feel like I've already kind of drawn out the mechanism for an acid. You can go ahead and put that together there. I drew it out in the last step. But I'm going to go ahead and just focus more on the base reaction, because I feel like a base reaction would be more efficient in terms of reactivity. And I'll explain what I mean whenever I draw out the mechanism. This is the mechanism by which we can use a base or an acid, well, not an acid, sorry, but which you can use a base, though, to convert an amide into a carboxylate. We have a nucleophile of an OH group that's going to come in and it's going to attack the carbonyl, moving electrons to the top. We get out of this, and this is an equilibrating reaction. I think you can tell where the directionality of this equilibrating reaction is going to be, though. Tetrahedral intermediate, this is the same thing that we've formed here, and the next step, in my opinion, is complete and absolute BS. To have, well, obviously once we knock the electrons up, they must come back down. This. So I have quite comically, or not even comically, this doesn't even do it justice, to show the efficiency of this reaction. This is going to form NH2, which I don't know if you remember, that's what we use to pluck protons off of terminal alkynes. This plucks protons off of sp3 hybridized carbons in certain circumstances. This is an extremely, extremely powerful base. And so it's going to do exactly what bases do, and it's going to steal the proton off of what is, in this case, is an extremely strong acid compared to him, thus giving us our equilibrating reaction here. It's very minor in reverse. Again, anything that involves this guy existing is going to be the minor at equilibrium, but what we form out of this is a carboxylate anion.